In Chapter 3, we finally get to what I would call the meat of calculus. We're going to be learning many different rules of how to take the derivative. Recall in Chapter 2, we used the definition. Well, now we get to use the shortcuts. So the first two rules we're going to learn is the constant rule and the power rule. The constant rule is the easiest because if you remember, the derivative is the slope of the tangent line. Well, if your function is a constant, which is a horizontal line, then the slope is always 0. And so whenever you take the derivative of a constant, you will get 0. So now you will see this type of notation, and that is going to be read the derivative of c with respect to x. This tells you what is your variable, and it equals to 0. Right? Another notation that we saw in Chapter 2 for the derivative was the function with one little accent mark, if you will, or one prime, but we call that f prime, or the derivative of f. All right, and so if f of x is a constant 365, then the derivative is 0. All right? Whether the function is positive or negative, that's still a constant. You don't see any variables. It would be 0. Let's just throw in one more. That's not a variable. That's just the number pi, approximately 3.14. Sometimes they throw that in to try to confuse us, but again, it is a constant, and so its derivative would be 0. Now, obviously your homework can't be all about that. We then have what's called the power rule. All right, when you have a variable raised to a power, you're going to take that power and multiply it by the original variable raised to 1 less degree. So let's practice it on some easy examples. The derivative of x to the 12th, what I say is you bring down the 12 in front, then write down your variable, and then subtract 1 from the original power. Alright, so let's see. We bring down the 0.5, and then we subtract 1 from 0.5. So if I subtract 1, I'm going to get negative 0.5. Right? Now what happens if there's already a number in front? Well, you keep that number, and then you're going to find the derivative of just x to the 6th, and so you'd bring the 6 down, the x, and again subtract 1 from the exponent. And so then to finish it off, we would multiply 5 times 6 and get 30 x to the 5th. So that's a very easy rule. Let's see if it could get more complicated. Not really, except for the different types of exponents. All right, so again, this problem, this is a constant, but we're not taking the derivative of just that constant. Notice we're finding the derivative with respect to h, so h is our variable. So just like in the above example where there was a 5 in front, we're going to take 3/5 pi, leave that, and take the derivative of h to the 5th, which would be 5 times h to the 4th. And then we would simplify that and get 3 pi h to the 4th. So if there is a number in front, you just leave it there and it's going to be multiplied. All right, so let's look at this. We keep the 9, and again we're finding the derivative of x to the 1/3 power. So we bring down the 1/3, and then we subtract 1 from 1/3, which would be negative 2/3. So again, I'm going to multiply 9 times 1/3 and get 3, and that would be my final answer. Okay, so now you're going to see square roots and cube roots and things like that, and automatically you have got to remember that the square root is the same as the 1/2 power. If you see the cube root, that is the same as the 1/3 power. All right, So once you've changed those radicals or square roots into exponents, then proceed with the power rule. So again, I leave my 3 and I'm going to find the derivative of x to the half. So I bring down the half, then I subtract 1 from a half, I get negative a half, and then multiply those numbers together. All right, so you can see in these next two examples we have a square root and we have a cube root, but in the denominator. All right, so this time our variable is u. So let's just rewrite this. First of all, the square root is the half power, but it's in the denominator. We don't want that. All right, so if it's in the denominator, you can move it to the numerator by changing the sign of the exponent. Hopefully you remember that from previous algebra classes. Once you do that, then you can find the derivative by the method, what's called the power rule. And so we would bring down the negative 1/2, and then we subtract 1 from a half, and that's going to be negative 3/2. All right, we're going to rewrite this. The cube root of x is x to the 1/3 power, and then just as we saw in the previous example, we're going to take that variable and move it upstairs by changing the sign of the exponent, because the power rule is only applied if it's x to a power, not 1 over x, but x to a power. All right, so our derivative, we keep the 5, we bring down the negative 1/3, we subtract 1 from a third and get negative 4/3. Right, then we would multiply those numbers together, and that would be the derivative. So now we have an example with some decimals. Same thing, we keep the number in front, we bring down the exponent, and then we subtract 1 from the given exponent, and then we would multiply that together. And I believe we would get negative 0.26 x to the negative 2.3 power. That's just an exercise in decimals. All right, so now we're going to start seeing a polynomial, more than one term. How do we find the derivative? Good news is you just take the derivative using the power rule or the constant rule in each part. All right, so the derivative here, we're going to take the derivative of that one. All right, so we have negative 5 times 4 times x to the 3rd power. We would subtract 1. Right, now we're going to do to that one, so that's going to be plus 3 times x squared. Then the next one, so that's going to be plus 2 times x to the 1st power, because 1 less than 2 is 1. And then you should remember that the derivative of a constant is 0. Now, of course, you shouldn't write that 0, but I just want to emphasize the derivative of a constant is 0. And now to clean that up, that would be the final answer. I want you to notice the original function was a polynomial. It was of degree 4, and when we took the derivative, we ended up with 1 less degree because of what that power rule says to do. All right, so now this one again is an exercise in decimals. So we keep the number in front, we bring down the exponent and do 1 less than the exponent. Number in front, bring down the exponent, 1 less. Number in front, bring down the exponent, which is a 1. Ooh, but what happens when I take 1 away from 1? Well, I get 0. And then, of course, that is 0. So let's see. Let's clean that up. This is equal to just 1. X raised to the 0 power, really anything except 0, raised to the 0 power is 1. And that is our derivative. Okay, then you'll start seeing problems like that. Well, we will learn what's called a quotient rule, but we don't need that. What we can do is we can rewrite this and divide each of these by x. So that would be 3x cubed. Again, if you divide x to the 4th by x, then x cubed divided by x would leave me x squared. then x squared over x is x. X over x would cancel out. And then the last one would be 10 on top of x. Well, we don't have a rule for that yet, but even when we do have a new rule, this is still the easiest one, is that when the variable is on the bottom, you can pop it up to the top by changing the sign of the exponent. Remember, there's a power of 1 right there. Okay, so that is the function rewritten as a different way. Now to take the derivative. Okay, I want you to notice when we get to x, there is a 1 in front, so I bring down the 1 and then subtract 1 from the exponent. So when you're doing the power rule, you're always going to have 1 degree less. And so if you just have an x, 1 degree less is no x's. Now we have a bunch of fractions, and so we're going to do the same thing. Subtracting 1 from 4/3 is going to leave me 1/3. Subtracting 1 from 3/2, which is 1 1/2, is going to leave me a half. And then the derivative of the constant, of course, is 0. Okay, now this one's a weird one. We could distribute it, but how about let's just leave the negative 1/3 and take the derivative of that part. So we bring down the negative 3. Subtracting 1 from negative 3 gives me negative 4. Then I'm going to bring down this minus sign. Then I have negative 6 because that comes down in front. X and 1 less would be negative 7. So let's see, I have a negative 1/3. Negative times negative is a positive. And we have that answer, which would be fine. But I'm going to go ahead and now distribute because these are both divisible by 3. So that's going to be positive that negative 2x to the negative 7. But I believe I would count either one of those answers correctly. I hope the computer does also. Let me know. All right, so now we have all of those variables in the denominator. So just like we've done, we want to rewrite that by popping it up to the top, by changing the sign of the exponent, and then taking the derivative. Just remember, when you subtract 1 from a negative, you get a bigger looking negative number. So now they're asking us to find the derivative evaluated at certain numbers, right? So that's two separate problems. So first of all, let's just find the derivative. Just as we turn square roots into a half power and cube roots into the 1/3 power, it might be beneficial, since we're plugging in numbers, to know that x to the 1/3 power is the cube root of x, and x to the half power is the square root of x. Now, I think about that in my head. I don't necessarily always write that down, but I think in this case it's going to help. So we want to evaluate this function at 64. So I want to take the cube root of 64, and I need to take the square root of 64. Well, it just so happens the cube root of 64 is 4, and the square root of 64 is 8. So I get, what, 16. Let's see, 2 goes into 8 4 times. That should be -20. All right, so now I'm going to come back here. Remember, that's my derivative. And I'm going to find now the derivative evaluated at 4. Now, I don't know a cube root of 4. It is just the cube root of 4. But the square root of 4 is 2. And that's how I would leave my final answer. Okay, so now we're back to how the end of chapter 2 stopped. Also, you might recall we had some problems like this on the last test, but instead of using the definition of the derivative, now I can use my power and constant rules. Right? So it says to find the slope and an equation of the tangent line. Okay, when you see the word slope, you need to think derivative. Slope is the derivative. Now hopefully you're going to get past writing that. When you see a number in front of x, when you take the derivative, it's just going to be the coefficient. Okay, so that is my derivative of that function at any point. Now it wants us to find the slope at this particular point. Remember, this is x and this is y. So I'm going to plug in -1 for x. Okay, and that is my slope of my tangent line. And now I have a slope and a point, and I'm going to use my point slope formula. Oops, sorry, this should have been up here. And then when I subtract my -1, that should be +1. And then I'm going to go ahead and clean that up, and I'm going to multiply everything by 3. And there's my equation of my tangent line at that particular point. All right, then you'll have a problem that asks us to find the points on the graph where the tangent line is horizontal. Well, when the tangent line is horizontal, that means the slope is 0. So another way of writing this problem would be to find the derivative and set equal to 0, solve for x. Believe it or not, that's what it says. Okay, so we want the tangent line to be 0, so we want the slope to be 0. So first of all, let's find the derivative in general. So that's my derivative. Now I want to know when that derivative equals to 0. So I would set it equal to 0, factor out an x. Then I'm going to set each factor equal to 0 and solve for x. And so find the points on the graph where the tangent line is horizontal. It's when x is 0 and when x is 8/3. Now, since they don't just ask for the x value and they ask for the point, they also need to find the y value associated with that. Now, we want it on the actual graph, so we need to come back up there. All right, so we're going to take the function and evaluate it at 0, which of course is 0. So one point is 0, 0. Then I'm also going to take 8/3. Okay, so the other point on the graph, and when x is 8/3, y is -256/27. It doesn't say to do this, but let's just look at what does this graph look like. This is what this graph looks like in general. I kind of missed it a little bit, but when it asks where's the slope of the line horizontal, at the point 0, 0, that's really the point 0, 0. If I were to draw a tangent line, it would be horizontal. And then here's the point, believe it or not, 8/3 -256/27. And that would be a horizontal slope. So what we're going to start finding out is those where the tangent is horizontal is at the peaks and valleys of our graph. On this last problem, we're talking about a demand function for a cell phone given by this, and that's 140, where x is the quantity demanded in thousand and p is in dollars. So part A, very easy, find the derivative. So we would just use our power rule combined with our constant rule. Okay, notice when I got to the 1.5x, I know that 1 degree less than x is no x's, and so I just get that coefficient. And so that's my derivative. Now, what is the rate of change? And rate of change is still that derivative of the unit price when the quantity demanded is 8,000 units. Now, the quantity demanded is x, but since it's in thousands, we need to let x equal to 8. So I'm going to take the derivative and evaluate it at 8. And I get -6.1. What does that mean? It means that the price is decreasing because of negative. It's decreasing -$16.10 per 1,000. So as they are making it, the price, as the demand increases, the price decreases. All right, now in part C, what is the unit price at that level of demand? Well, if you go back to the problem, P was the unit price at that level of demand, meaning let X be 8, which represents 8,000 cell phones. And so we're going to evaluate the function at 8, and I get $81.60. And so when the demand is 8,000, that's the price. But remember, as we sell more, the price is decreasing.